Hello everyone, welcome to the first video of calculus. In this video, I'll be explaining the concepts of limits. Before starting this video, I must inform you that this video is specially for maths honors and B.Tech students, but anybody who needs to learn graduation level of calculus can learn from this video. So let's start it and happy learning. First of all, we'll discuss about limits. Limit of a function. The notion of limit of a function is very fundamental in the study of calculus. Roughly speaking, a function fx approaches a limit L, as you can see in the diagram. This curve represents a function. Okay, so this is a function. A function fx approaches a limit L. It means it tries to become L as x approaches c. That is, as x takes values nearer and nearer to c, fx also takes values nearer and nearer to L. Here you can see that the x is going nearer to c. This value of x can never become c, but it will go as near as possible to c. Now in this case I've taken x a bit too far from c, but in actual it is very close to c, but for explanations I've taken it here. Now let's say this is x, and for this value of x, let the value of function is fx. So this is the value of function, that is fx. Okay, as x approaches c, the value of function approaches x. As it will go nearer and nearer to c, the value of function will go nearer and nearer to the value equal to L. Okay, through this diagram we can define limit as follow. A function f is said to tend to a limit L. A function f is said to tend to a limit L as x tends to c if given any epsilon. Now what is epsilon? Epsilon is this small distance between L and fx. You can see if x is very close to c, fx will be very close to L, and therefore the distance between L and fx, or difference between L and fx, will be very small. And this small difference is denoted by the symbol epsilon. Epsilon is always greater than 0, and it could be very small. There exists a delta. Now what is delta? Delta is the difference between x and c. Okay, and of course this delta is also very small, greater than 0, and it also depends upon epsilon. So a function f is said to tend to limit L as x tends to c if given any epsilon greater than 0. There exists a delta greater than 0. So if we take any epsilon greater than 0, there must be a delta greater than 0. For further explanations, let us see how we can write it as fx minus L modulus. It means difference of fx and L is less than epsilon whenever difference of this x and c is less than delta. We are going to take an example. Let us take a function is equal to x square. Now for x is equal to 3, we all know that the function has the value 9. If we take the value 3 and put it here, the function has the value 9, but we'll do it by the method of limits. Now let us take x is equal to 1. If we take x is equal to 1, the value of function will become 1, and this thing modulus fx minus L will become, the value of fx is 1 and L is 9. As we can see, f3 is equal to 9, so this is L. So fx minus L modulus is 8. Now for the next value, x is going closer to 3. So for the next value x is equal to 2, the function will be 2 square, that is 4, and modulus fx minus 9 will be equal to 4 minus 9 modulus equal to 5. Now we'll go nearer to 3, x is equal to 5 by 2, that is 2.5. The value of function will be 25 by 4, and again modulus fx minus L would be 2.75. I have already calculated for you. Then for x is equal to 11 by 4, we are nearer to C, that is 3. The value of function is this, and modulus fx minus L is this, and so on and so on. We can go as nearer to C as possible, and we can see that modulus fx minus L, that is epsilon, the value of epsilon is coming closer and closer to 0. Therefore we say that epsilon is very small but still greater than 0. We can see that as x approaches towards 3, the function approaches towards 9. Yes, so this is the basic definition of limit. It means a function f is set to tends to a limit L. A function tries to become L as x tries to become C if fx minus L modulus is less than epsilon whenever x minus C is modulus is less than delta. Excuse me. And this delta depends upon epsilon. I hope this definition is clear. Now, we have a few questions out here and we can solve them. Let us take the first question. Now, the first question, limit x tends to 2, x square minus 4 upon x minus 2. We need to show that it is equal to 4. Now, in the earlier classes, you must have learned that this can be solved like this. Limit x tends to 2. 4 can be written as 2 whole square. A square minus b square will become a plus b, a minus b. Cancelling out x minus 2, the value of the limit will become 2 plus 2, 4. Okay, but we can also solve it by the definition that we have just learned. Now, this is fx, this is L, this is C, this is x. What we do? First of all, function minus L is less than epsilon. Okay, and now we need to show that x minus 2 is less than some delta, and delta depends upon epsilon. Now, first of all, we'll write 4 as 2 square, and again we can do it like this: x plus 2, x minus 2, x minus 2. And now we have x2 minus 4, that is x minus 2. And now if you take epsilon equals to delta, yes, now you have proved that x minus c modulus is less than delta. Yes, so we started with function minus L is less than some epsilon. And after solving, we get that x minus c is less than some delta, and that delta is equal to epsilon. That delta can be equal to epsilon, epsilon square, epsilon root, epsilon by 2, 3, 4, anything. It depends upon epsilon. Okay, so some people may ask that if a question can be done in an easier way, why are we using this this a bit complicated method? Because there are a few questions which can be solved by only this method, not by this method. Okay, so we'll take a few more examples. Let us take the second question. The question is limit x tends to x sine 1 by x is equal to 0. We need to prove this. Okay, I'll cover it for you. Okay, Now, first of all, this is fx, this is L, this is x, this is c. So we'll start with fx minus L. Okay, so minus 0, it means this is x sine 1 by x. Then it can be written as modulus x modulus sine 1 by x. Now, as we know, sine theta modulus can have value less than equal to 1. Okay, so if we don't take the modulus, then sine theta can be from minus 1 to 1. But if we take modulus of sine theta, it is either equal to 1 or less than 1. Okay, whatever the value of theta might be, could be anything. Okay, this is some angle theta. So sine theta is always less than equal to some 1. Now if we multiply both sides by modulus x, what we are going to get is this. Now this is our fx minus L, so I can write it as this as well. Okay, now can we write this modulus x as x minus 0 modulus? You might be asking why. Most of you might have got it, because it will make it as x minus c. Yes, and this is fx minus L. Now if we take some delta here which is equal to epsilon, then what it will make? X minus c is less than equal to some delta which is equal to epsilon. Okay, and fx minus L is also less than this epsilon. Yes, so it is proved. If I'll repeat it for you, function minus L modulus can be written as this, because this is 0, modulus x modulus sine 1 by x. Now since sine theta modulus is always less than equal to 1, multiplying both sides with modulus x, now this will become your original fx minus L, and here I am writing modulus x as modulus x minus 0. Now I said that take delta equals to epsilon, so your x minus c is less than some delta, not equal, sorry, less than some delta, and your fx minus L is less than some epsilon, because delta is equal to epsilon, hence proved. So this is how we can prove by definition. Let us take one more question, and this question is, show limit x tends to 0 sine 1 by x does not exist. It does not exist. It means as x tends to 0, this function approaches to no definite point. I have tried its graph as well, and I found that as x approaches 0, the function starts, say, oscillating here and don't get to a finite value. Similarly, if we put the values from x, it means if x tends to 0 from right, it does the same, it vibrates here. Okay, so we don't get a finite point here at x equals to 0, therefore it does not exist. But how we are going to prove it that it does not exist? Let's do it. It's a bit complicated, but you'll get used to it. First of all, let limit x tends to 0 sine 1 by x equals to, let's say it is equal to some L. Then there must be some epsilon. Okay, so let's say there is an epsilon which is obviously greater than 0, and it must follow this definition that fx minus L is less than epsilon for x minus c, I can write it as this, greater than 0 and less than delta. Now I need to disprove it. Okay, so I'm going to take some values of x, like I'm taking x1 equals to 1 upon 2n plus half pi, and I'm taking another value of x, that is 1 upon 2n minus half pi. Now why I have taken these values, you'll get to know very soon. So I've taken two values of x. Okay, now if you try to find out sine 1 by x1, sine 1 by x1, it will be sine 1 upon this thing. So 1 upon this thing actually this denominator will go towards numerator, so it will become 2n pi plus pi by 2, and 2n pi plus theta, sine 2n plus pi theta is equal to sine theta, and the value is equal to 1. Similarly, if you find sine 1 by x2, that is sine now 1 upon 1 by this, so the denominator will go to the numerator, 2n pi minus pi by 2, 2n pi minus theta, fourth quadrant, it will be negative. These are the basics of trigonometry, so minus 1. Okay, so I have calculated sine 1 by x1 and sine 1 by x2. Now I'm going to put these values out here. I'm calling it equation number 1, and let's see what happens. Okay, you must have noted it. Okay, or shall I do it here? Yes. So I'm going to put it in equation 1. So from equation 1, this whole thing for x1 will become 1. So 1 minus L modulus is half. And similarly, if I put this value in 1, I'm going to get minus 1 minus L. Minus 1 minus L modulus less than half. And if I take negative common, the modulus will make it positive. So 1 plus L less than half. I hope you have got it. 1 minus L modulus is less than half, and 1 plus L modulus is less than half. Okay. Now if you see that 2 is equal to 1 minus L plus 1 plus L. Okay, if we add these two terms, cancelling L, we'll get 1 plus 1, 2. So 2 is equal to this much. And if I take the modulus as well, there will be no impact. Okay. Now, we can say that, now you must be aware of the fact that A plus B modulus is less than equal to modulus A plus modulus B. So if I take it as A and this term as B, modulus A plus B will become modulus A plus modulus B. Okay, but as we know from second equation that this thing is less than half, so this thing is less than, this thing is less than half, and this thing also is less than half. So therefore I've put a less than sign here, less than half, less than half, so it becomes 1. Absolutely absurd. It doesn't mean anything that 2 is less than 1, so we'll say that it is absurd, and therefore our assumption is wrong, and limit x tends to 0 sine 1 by x cannot be equal to anything. It does not exist. So a bit of a cracker. It is a tough question, so you need to just memorize this thing to disprove it, or else if you could think a bit more, you can take epsilon is equal to 1 by 3, and here also you can take it as 2n plus 1 by 3 pi, 2n minus 1 by 3 pi. It can be solved anyway, but this is the best way I found of solving this question. So okay, let's do something new in limits. Now the next topic we are going to have is, okay, before it we have another question, I guess. Yes, prove limit x tends to 0, sin x by x is equal to 1. So let us see. You must have studied this identity at your school, that limit x tends to 0, sin x by x is equal to 1. And now we are going to prove it. Okay, and let's see. It has a very beautiful proof. Let's see how we are going to prove it. First of all, we need to draw a circle of unit radius. Unit radius means a circle of radius 1. Now, in the first quadrant, at an angle x, I draw a line. Yes. And now, this point is A, this point is B, perpendicular, this point is M, and this point is C. Okay. Now, in this diagram, we will look at three main figures. First one, triangle OAB. Second one, sector OAB. And third one, triangle OAC. So this small triangle OAB, then this sector, and then this larger triangle. Now obviously the area of the smaller triangle is less than the area of sector, and then it is less than the area of the larger triangle. Okay. Now, here I have written it. Area of smaller triangle is less than area of sector, is less than area of larger triangle. Now, as we can see in this triangle, tan x is equal to perpendicular upon base. So, tan x is equal to y upon 1. So, here I have written as y is equal to tan x. And in parametric form, any point on the circle is represented as cos x sin x. So any point on this circle, like this point B, is represented as cos x sin x in parametric form. Okay, so any point B is cos x sin x. So if the point B is cos x sin x, it means that this length, okay, this is cos x, and this height is sin x. This height is sin x, this is cos x. Like if you take a point 2, 3, so it means this length is 2 and this is 3. So this is cos and this is sin. Okay, so BM is sin x and OM is cos x. Okay, now area of the triangle OAB. Triangle OAB means this triangle OAB. Area is half into base is 1, and height is sin x. Area of sector is half into radius into angle. Area of sector. And area of this right angle triangle is half into base into height. So half into 1 into y, and y is equal to tan x. Fine. Cancelling out 2 at the denominator. Then dividing by sin x, we'll get 1, x by sin x, tan by sin is sec, or 1 by cos. Okay. Now reciprocating it. Okay. When we reciprocate it, the signs will get changed. So see. Yes, reciprocal of sec is cos x. Now we did it to get sin x by x. Now as we know, as x tends to 0, cos x, that is this function, becomes 1. So as x tends to 0, cos x tends to 1. Or simply if x is 0, cos x is 1. Okay. So this function is squeezed between 1 and 1. It is greater than 1 and less than 1. It sounds a bit strange, but this is the fact. This function is greater than this function and less than this function. Now here we'll use a theorem called squeeze theorem, that if a function is squeezed between two functions and those two functions have same values, then the mid function will also have the same value. This is the squeeze theorem. Okay, so without proving it, we are using it. If a function is squeezed between two functions and both the functions have same values, then the mid function will also have the same value. Therefore, it will be equal to 1. Now, this is our answer. This is how we prove limit x tends to 0, sin x by x is equal to 1. And we are going to use this identity very often in the questions. Okay. Now, a few more topics. So, the next topic that we are going to study is left-hand limit. Okay, so left-hand limit, the concept is quite simple if you have understood the previous concept. It says, if a function f is said to tend to a limit L as x tends to c from left, if given any epsilon, this is delta as previous, and this is epsilon. Okay, by now you must know this. So I repeat, a function f is said to tend to a limit L as x tends to c from left if given any epsilon greater than 0, however small, same definition as previous. There exists a delta depending on epsilon such that fx minus L, that is this minus this modulus, is less than epsilon, and x is somewhere between c minus delta. Obviously this length is delta, so this point is c minus delta. So x is somewhere between c minus delta and c. X is somewhere between c minus delta and c. In left hand limit, x approaches c specifically from left hand side. Okay, so this is the definition for LHL. We'll not be using this definition in any of the question, but it is important to understand. Now, right hand limit has similar definition. Let me state it once. A function f is said to tend to a limit L as x tends to c from right. Now you can see clearly what this definition is trying to say. If x approaches c from right, okay, and like before, this is fx. Okay, so I repeat, a function f is said to tend to a limit L as x tends to c from right if given any epsilon greater than 0, however small. There exists a delta greater than 0, and you know what, x lies between c and c plus delta. C and c plus delta. Okay, so this is the definition of right hand limit. Okay, there are two remarks. First one, if LHL, that is left hand limit, is equal to right hand limit, then we say that limit exists and is equal to L. If LHL is not equal to RHL, then we say that limit does not exist. Okay, as you can see from the left, the limit is L1, that is function is approaching L1 near C, and from right hand side, when x approaches from right, the function tends to limit L2. Both are not equal. Yes, in this case both were equal, but in this case both are not equal. Equal means left hand function and right hand function are going to meet together at C. They might not meet, but it seems that they are going to meet. And if they are not equal, it means one from left hand side the function is approaching a different point, and from right hand side the function is approaching a different point. Both have a gap between them. Okay, so here we can see that. So this is a right hand limit. Now we have a few questions out here. Is this okay? We need to check its limit at 2 points, 1 and 3. This is the question. So first of all, we need to understand what it means. It means at when x was less than 1, here, when x was less than 1, the value of function was x plus 2. When x was from 1 to 3, the value of function was 4x minus 1. And when x was greater than 3, the function had a value x square plus 5. Okay. So if the x is less than 1, the function has this value. If x is from 1 to 3, the function has this value. If x is greater than 3, then the function has this value. Now, if you need to check the limit at point 1, first we'll find out left hand limit, then we'll find out right hand limit. If they both are equal, then we'll say that limit exists, and similarly at point 3. Okay, so first of all we'll check at 1. So we'll write it as limit x tends to c minus, and from left side the function is this. Now we can simply put x equal to 1 and it will become 3. There is another way of solving it by the definition of h.